Hi, in this lecture, I'm going to talk about groundwater flow and well hydraulics. And this is a part of our bachelor level course on groundwater hydrology. Okay, so by combining the Darcy's law, which we discussed in previous lectures, and the conservation of mass, we can derive the general equation that is used to describe flow in groundwater. Okay, so if you consider here this control volume here, based on conservation of mass, using conservation of mass, you can write M in minus M out is equal to delta M. Here, M in is the mass entering this control volume, the total mass entering this control volume minus the total mass exiting this control volume, M out is equal to the change in the mass in this control volume. Okay, so if you represent the velocity in the x direction by qx, the velocity in the x direction on this side here will be equal to qx plus the derivative of qx with respect to x times dx. Okay, and let's represent that by qx plus dx. And I didn't want to make these figures too crowded, but you can write the same equation here. You can show the same velocity component for the y direction and for the z direction. So the velocity qy plus dy will be equal to qy, velocity in the y direction, plus the derivative of the velocity in the y direction with respect to y times dy. And the velocity qz plus dz in the z direction will be equal to the qz plus the derivative of the qz with respect to z times dz. Okay, and so in terms of the mass entering this control volume, you need to multiply this velocity that has the unit of length per time times the area to give the volumetric flux. Okay, and then you multiply that by density, okay, to get the mass flow rate, and then you multiply it by delta t by dt to get the mass. That is the mass entering this control volume in the x direction, from the x direction. You can do the same for the y direction and for the z direction, and that is the M in. Okay, you can do exactly the same for the M out. The only difference here is instead of qx, you basically use this this three equation we wrote here. That is, instead of qx plus dx, instead of qx, you need to write qx plus dx. But qx plus dx is equal to qx plus the derivative of the qx with respect to x times dx. Okay, and if you plug these definitions of the velocity into this equation, you get M out that will be equal to, that is for the x direction, y direction, and z direction. So you have now an equation for M in, you have an equation for M out, and also for delta M, the change in the mass in that control volume, you can easily show that that is equal to the density times the specific storage, SS, that we had in the previous lecture, the definition of SS, times the derivative of the pressure head with respect to time times the volume, that is dx, dy, dz times dt. Okay, you can easily actually evaluate and see this has the unit of mass, because look here, SS is volume divided by volume times the decrease of the head, right? So basically, therefore this one has the unit of 1 divided by length. And if I multiply that by dh over dt, so the whole thing here will be will have the unit of 1 divided by time. And if I multiply by this time, so the time will go out basically. So this term, and this term will be basically dimensionless. And then here you have dx, dy, dz that has the volume of the dimension of the volume times density. We know that that will be equal to the mass. So you can as well evaluate this equation like that. Anyway, so you have now equation for M in, you have equation for M out, and you have an equation for delta M. If you plug these three terms that we obtained here into this equation, you can show that minus derivative of qx with respect to x, minus derivative of qy with respect to y, and minus derivative of qz with respect to z is equal to ss derivative of the pressure head with respect to time. Okay, that is very easy to calculate. Look here, if you write M in minus M out, this rho qx dy dz dt will be out by this rho qx dy dz dt. You see, and this one will be out by this term, and this one will be out by this term. And then and then also the dx divided dz will be out by this dx divided dz here and from the other side of the equation. So it's a very simple algebra. You can easily derive this equation. And so now we have this equation here that is derived from the conservation of mass. Here, for Qx, Qy, Qz, we have Darcy's law. So instead of Qx, let's write, by the way, here, you notice here that the density was inside this derivative, but now I take it out. In other words, we're assuming a density is constant, okay? And that's why you don't see the density here in this equation, okay? There's no density because we assume density is constant. And if you assume density is constant, so the rho, each of these term basically has density. You see here, M in had the density, M out has density, delta M has density. The density basically cancels out from each side of the equation. Okay, anyway, so instead of Qx, I write the minus Kx, derivative of h with respect to x, with respect to y, with respect to z. Okay, and then all I need to do now is just instead of so that will be minus derivative of Qx with respect to x. Instead of Qx, I write this equation. So minus times minus will be positive. So that will be derivative with respect to x, Kx, derivative with respect to derivative of h with respect to x here. Okay, and then the same goes here. So I have rho, the derivative with respect to y, it's here. Instead of Qy, I put this term. Okay, and minus by minus will be plus. The same here. Again, derivative with respect to z is here. Instead of Qz, I write Kz times derivative with the derivative of h with respect to z. Okay, and that will be equal to Ss times derivative of h with respect to time. Okay, h with respect to time. And then if we assume, let me delete this one. It's a bit crowded. So if we assume the system that my medium, my aquifer is homogeneous, that means and isotropic, that means Kx, Ky, Kz will be the same, and let's represent them by K, okay? So therefore, I can divide all terms here from each side of this equation by the letter K, by the parameter K. Therefore, that will be the second derivative of h with respect to x2, second derivative of h with respect to y2, second derivative of h with respect to z2 will be equal to Ss divided by K, because I divided everything by K, times derivative of h with respect to time. And then, if you assume you're dealing with a steady state condition, this term will be equal to 0. Therefore, the second derivative of h with respect to x2 plus the second derivative of h with respect to y2 plus the second derivative of h with respect to z2 will be equal to 0. In other words, del square h will be equal to 0. And that is a beautiful equation that is used to describe the general flow in groundwater. Okay? And yeah, so now we have this equation. The flow condition basically differ for confined and unconfined aquifers because you will have a different boundary condition, and you will see it in the next few minutes. Okay, so we can now solve this equation for different boundary condition. Okay, so let's first consider this case. That is, let's assume groundwater flow with a velocity Qx in the x direction of a confined aquifer of uniform thickness. So that means I'm now solving this equation, the solution of this equation here, for confined aquifer, and it's a 1D flow. Since it's a 1D flow only in the x direction, that means this will be equal to 0, and that will be equal to 0. So you will have only the second derivative of h with respect to x2. Sorry, the second derivative of h with respect to x will be equal to 0. Okay, so the second derivative of h with respect to x will be equal to 0. Okay, so we are dealing with a confined aquifer and the flow in the x direction. Therefore, this is an easy integral. Therefore, you can conclude here that the derivative of h with respect to x should be a constant, and you can take one more derivative, one more integral here that will be the parameter h here will be equal to c1 times x plus c2. Okay, but obviously you need to calculate the constant of the integral here, that is C1 and C2. So from Darcy's law, we know that Q, the velocity is equal to minus K times the derivative of h with respect to x. In other words, the derivative of h with respect to x is equal to minus q divided by k. That is from Darcy's law. And then when you look at this equation, if you take the derivative of h with respect to x, the answer will be c1. So in other words, minus q divided by k should be equal to c1. So that we already have that one. And also for the second constant of the integral c2, we just assume at x equal to 0, the h is equal to 0. And if you put here x equal to 0, h equal to 0, that means c2 will be equal to 0. c2 will be equal to 0 here. And so now I have this parameter c1, I have the c2, I plug these two into this equation. Therefore, you can show that h, that is the head, is equal to minus q, that is the velocity, times x, that is the distance, divided by k. Okay? And so yeah, that is the flow equation for confined aquifer when you're dealing with when the aquifer has a uniform thickness, and also you're dealing with the 1D flow in the x direction. Okay, so so let me read it from here. This states that the head decreases linearly with flow in the x direction. As you can see here, if you plot this line, you see it's a linear line. If you plot h with, versus x, you see it will be a linear line with the slope of minus q divided by k. And yeah, in the x direction, the head is decreasing linearly. Note that the yeah, so here actually this picture is so this is you're dealing with a confined aquifer. I say it is confined because it is confined by two impermeable layers. As you can see here, this is impermeable from bottom, and from top, right? And then the head here is a straight line. And if the flow is in this direction, the head here linearly decreases as with the flow in the x direction. Okay, and if you remember in the previous lectures, we defined what is the piezometric surface. That is, note that the water level in a well penetrating a confined aquifer. Here you see here, this is a well penetrating this confined aquifer. The water level in a well penetrating a confined aquifer defines the elevation of the piezometric surface at that point. Okay, so that is basically the head in that particular point. Okay, so here this is the piezometric. And the head, this is the piezometric head, and you connect them to each other. This gives you the piezometric surface. We had defined that in one of the previous lectures. Anyway, so that is the equation for the flow, 1D flow in confined aquifer with constant thickness. Okay. So there is an example here. This is quite a straightforward example. So let's solve it together. That is, if the distance and the observed piezometric surface drop between two adjacent wells are 1,000 and 3 meters respectively. So you have two wells that are 1,000 meters away from each other, and the drop in the piezometric surface is 3 meters. Okay, that's the question. So basically here, let's say this is the first well here, and I have the second well. The distance between these two wells is 1,000 meters, and the piezometric surface drops 3 meters, as you can see in this picture. So what's the question? Find an estimate of the time it takes for a molecule of water to move from one well to the other. Okay, there are a couple of assumptions here. Assume a steady unidirectional flow in a homogeneous silty sand confined aquifer with a hydraulic conductivity of K equal to 3.5 meters per day and an effective porosity of 35%. Okay, so you just simply need to write down this equation that we just derived. That is, H is equal to minus Q times X divided by K. Therefore, Q, the velocity, will be equal to H times K divided by X. And you have all these parameters. You have the H, that is 3 meters. You have the K, that is given in the question, 3.5 meters. X is 1,000 meters. And this, so you see here, for H, I put minus 3 because it is dropping, right? So that's why I put minus here. So minus times minus will be positive. So anyway, the velocity, Darcy velocity, will be this one, okay? And if you remember in one of the previous lectures, I explained that to calculate the arrival time, you need to work with the pore water velocity. And pore water velocity is equal to Darcy velocity divided by the porosity. And we do that because water only flows through the porous space. So you need to divide Darcy velocity, which is the average velocity across the entire surface, by the porosity to get the pore water velocity. And if you do that, so Q is this one, you already put it here, and the porosity was given in the question, that is 0.35, and that gives you the pore water velocity, that is 0.03 meter per day. And the question was how long does it take to travel this 1 kilometer distance? So from physics, we know that the velocity is equal to length, the distance divided by time. Therefore, time will be equal to the distance, that is 1,000 meter, divided by velocity, which is 0.03. And then I'm just expressing my answer in year. Therefore, I divide everything by 365, or multiply this by 1 divided by 365 to convert a day to year, and the answer will be 91.3 years. So it will take almost 91 years for the water molecule to move from one well to the other. Okay? So that was the story about flow in confined aquifer. But of course, you are as well sometimes dealing with unconfined aquifer. Okay, so flow in unconfined aquifer is inherently difficult to characterize because the position of the upper boundary layer, if you upper boundary or the water table, remember the unconfined aquifer at the top, you had the water table that separates the saturated zone from the unsaturated zone. Okay. And since that boundary, that boundary or that water table is not fixed, so things are more difficult with the unconfined aquifer. Okay, and groundwater flow problems in which one boundary is a free surface can be analyzed on the basis of Dupuy theory of unconfined flow, okay, which is who was a French engineer. So he had three basically assumptions here, and we will implement these assumptions in our analysis. That is, the assumption is that the contour volume we consider extends from a horizontal impermeable base, like this one, the black base here, that's impermeable, in the XY plane up to the water table. So that is this, if you remember, this sign indicates water table. So the contour volume extends from the horizontal impermeable base to the water table. That's first assumption. The other assumption is that no velocity component in the vertical direction. So you don't have the QZ anymore. So everything is in the horizontal direction. Okay, that means you have QX and QY, but not QZ. And also the head gradients are assumed to be equal to the slope of the water table. So you have these three assumptions. We are making these three assumptions. So now you can apply the conservation of mass again. That is mass in, M in minus mass out is equal to delta M. Okay. I just present the final equation. So I don't go through the derivation. You can find this derivation almost in any hydrology textbook. Okay. And I thought it's maybe not that necessary here to go through the derivation. So I'm just showing the final equation. So if you apply the conservation of mass, and if you consider these three assumptions, you will end up with this equation, which is actually, which is basically, again, the combination of the conservation of mass and Darcy's law, which provides you an equation that can be used to describe flow in homogeneous and isotropic unconfined aquifer. Okay, so that's the equation. In this equation, you have two terms here. The rest is the same as before. That you have the K, the other parameters I meant. The K is the permeability, hydraulic conductivity. H is the head, pressure head, and you have two new terms here. That is Ri and Sy, and Ri is the net rate of recharge, okay, to that aquifer, and Sy is the specific yield, which we defined before in the previous lectures, in one of the previous lectures, as the volume of stored water discharged per unit surface, per unit decrease of water table, or per unit decrease of the head. Okay, so you had this definition before. Okay, so in the case of a steady state condition, like we did this assumption in the past, this term will be out, will be equal to 0. Okay, so therefore 2Ri divided by K, that is the hydraulic conductivity, plus the second derivative of H with respect to X, plus the second derivative of H with respect to Y will be equal to 0. Okay, and this is the equation that can be used to describe flow in homogeneous and isotropic unconfined aquifer under a steady state condition. Okay, so so now there's an example here. I wanted to go through the example so you will see how to apply this equation. The example is calculate the groundwater recharge into two long parallel streams completely penetrating an unconfined aquifer with a continuous recharge rate W occurring uniformly above the aquifer as illustrated in the figure. Assume one directional flow and that two-point assumption are valid. Okay, so these are the two rivers you have. Okay, that's the cross section. They're like flowing perpendicular to this screen, and that is your aquifer here. Okay, so the question is calculate the groundwater recharge into these two streams. If you have this continuous recharge rate to the aquifer that is represented by W. Okay, so to solve this example, you can literally just write down that equation that we just mentioned in the previous slide. Here, the question says assumes one directional flow. So that means one term is out here. Let's say this is out. Okay, so you will have only 2W divided by K plus the second derivative of H with respect to X will be equal to 0. Okay, and then you can easily calculate this differential equation, and the answer will be H2 will be equal to minus W divided by K times X2 plus C1 X plus C2. Okay, you just take this, the integral of this equation 2 times, and then here you have two constant of the integral C1 and C2. So, but you have the good news is you have the two boundary condition that is here. That is here at X equal to 0. H is equal to H1, and at X equal to L here, H is equal to H2. Okay, so I have this two boundary condition at X equal to 0, H is equal to H1, at X equal to L, H is equal to H2. And if I plug these two condition into this equation, then you will have two equations and two unknown. Then you can calculate C1 and C2. And if you plug it back to the same equation, you will arrive, you will obtain this equation basically. Okay. That relates the pressure head to the K and to the length and to the H1 and H2 and the recharge to the aquifer. Okay, as a function of the X as a function of distance X from the origin. Okay, and sometimes as well the discharge Qx per unit width or thickness at any distance or desire to calculate, and that can be calculated by you just multiply. Basically, you have the Darcy law that is minus K dH over dx. Okay, that is the Darcy's law. You multiply it by the H. Okay, because this is the discharge per unit width. Okay, and that's why, because the Darcy's law, the velocity has the unit of length per time, you multiply it by another length here, therefore the unit of this Qx will be L squared per time. Okay, so this is the discharge per unit width. Okay, and then so dH over dx you can easily calculate by this equation. You have already the equation, and then you multiply it again by the H, and if you do the mass, you will end up with this equation. Okay, Qx will be equal to this term. That is that relates the discharge per unit width to K, H1, H2, L, and W at any given distance X from the origin. Okay. And then, but again, I just wanted to emphasize once again that in this equation, Qx has the unit of L squared per time, and H1 and H2 has the unit of length, and K and W here, they are the K has the and W, they have the unit of length per time. Okay. Sometimes as well, we wanted to know what is the maximum height of the maximum elevation of this water table, that H max here, as you can see here. That is called groundwater divide. And also we wanted to know where's the location of that. And using this equation, we can easily calculate that. Basically, we know that at the maximum here, the dH over dx is equal to 0. And from the Darcy's law, so since Darcy's law is the basic gradient of the head, and since at that point the gradient of the head is equal to 0, that means velocity will be equal to 0. Okay, so that means at that point qx is equal to 0. Then you can rearrange this equation and calculate the x value at which qx will be equal to 0. Okay, because if this is equal to 0, all you need to do, you need to divide everything by w here, right, and bring the x to the other side of that equation. Then you will obtain this equation that gives that d here, as you can see in this picture here, is the location at which the maximum water table elevation or groundwater divide occurs. Okay, and then the value of the H max now, since you have the d, or you have the x value, you can plug it here in this equation, and then you can calculate the value of the H here, the maximum value, which will be equal to this one. So this is another useful equation. Okay, yeah, so there is a example here. I want to go through that example. It's very actually just simply the application of this, that simply shows you the application of the equations that we just derived. So that is an unconfined aquifer of clean sand and gravel is located between two fully penetrating rivers and has a hydraulic conductivity of 0.01 centimeter per second. The aquifer is subject to a uniform recharge of 1.6 meter per year. The water surface elevations in river A and B, so this is river A and this is river B, are 8.5 and 10 meters. So this is given. So H2 is equal to 8.5 and H1 is equal to 10 meter. Okay, 10 meter respectively above the bottom. Estimate the maximum elevation of the water table, that is H max. So you have an equation for that, and the location of the groundwater divide. Again, you have an equation for that. That is the D. The second part of this question is the travel time from groundwater divide to both rivers. Okay, so wherever is the groundwater divide, let's say for example it's here. If you calculate, so the question is what's the travel time from here to river B or from here to river A. So that's the second part of the question, assuming the porosity is 35%. And the third part of the question is the daily discharge per kilometer from the aquifer into both rivers. Okay, so you just need to write down that equation we just derived for the section A, that is D is equal to this equation. So you have all the parameters here. The length is already given, that is the 460 meter, and K is given in the question. I just converted the unit to meter per day. Okay, W, the recharge rate has been given already, that is here, and then you have 2, and the two is here. Okay, there's 1, 2 for this one, and the other one is here. L already given, H1 given, and H2 as well given. Okay. Yeah, because H1 and H2, yeah, that's correct. H1 and H2 was given 10 meter and 8.5 meter. Okay, so if you do the algebra here, you will get 171 meter from river B. The X will be equal to 171 meter. Okay, so that means if this is where the maximum occurs, this distance is equal to 171 meter from the origin. Okay, from the origin. Let me close this one. Sorry. Okay, perfect. I think yes. Okay. So we calculated the location of the H max. Okay, so now the other part of section A was that what's the maximum elevation of the water table. Again, we have an equation for that, as you can see here. This is the equation, so therefore H max will be a square root of this side of the equation. Okay, and that's literally what we're doing here. And again, you have all these parameters. H1 you have, H2 you have, D you already calculated here. That is 171 meter. W given in the question. K given in the question, L given in the question. You just plug all the values here, and you will see H mass will be equal to 10.7 meter. Okay, that will be the maximum elevation. Okay, so the second part of this question was about what's the basically, let's read the second part of the question was the travel time from groundwater divide to the both rivers. So let's first calculate the time to river A. So first we need to calculate the pore water velocity like the previous example, because travel time is about pore water velocity. And then you knowing the distance, you can calculate the time. So this is the Darcy velocity, right? And I divide it by the porosity to get the pore water velocity. So the pore water velocity therefore will be equal to 1 divided by the porosity that is given in the question times minus K, and K is equal to 8.64. That is again given in the question, right? Times delta H over delta X. So we are here, we are here, and we just calculated this height is equal to 10.7 meter. In the question, it's given that this height H2 is equal to 8.5 meter and H1 is equal to 10 meter. And we know this distance is 171 meter. Okay, so therefore VA, the pore water velocity toward A will be equal to 1 divided by porosity times K is given in the question times delta H over delta X. Delta H here 10.7 minus the H here 8.5 divided by the X of this point minus X of that point. So X of this point is equal to 171 minus X of that point, that is 460. If you do the calculation, you'll end up with 0.19 meter per day. So that's the velocity. Therefore, the arrival time or the travel time. What was the term I used? The travel time will be equal to the distance divided by pore water velocity. And the distance here is, we know the total distance is 460 meter and this is 171 meter. Therefore, this distance LA will be equal to 460 minus 175 divided by the velocity we just calculated, and that will be 1524 days. Okay, or in other words, 4.18 years. Okay, that will be the travel time from the water table divide to river A. And you can do exactly the same for river B, that is the VB is equal to 1 divided by porosity, which is given, times minus K, that is given, times delta H over delta X. Okay, and delta H here I have 10.7 minus the H1 here is 10 divided by 171, that is the X of this point minus X of this point. And here is at the origin, so that is 0. Okay, and that will be equal to minus 0.101 meter per day. You see here in this question, the X direction is considered in this way, as you can see here, right? So the minus sign, that means the flow will be in this direction, right? And which kind of makes sense because here you have a higher head, 10.7, than H1, that is 10 meter. And for the travel time, again, will be equal to the distance divided by velocity. Here we know distance will be equal to 171 meter divided by velocity, which will be equal to 1693. Okay, days, which will be equal to 4.64 years. Okay, and then the third part of the question had 3 parts. The third part was the daily discharge per kilometer from the aquifer into both rivers. Okay, the daily discharge from the aquifer to the rivers. Okay, so for river B, so river B is located at the origin, therefore X is equal to 0. We have this equation to calculate the discharge. Again, you have all the parameters here, except you need just to put here X equal to 0. So you have the K, you have the H1, H2, WL, and everything. You put it here. That will be the QX. Okay, and remember that was the discharge per width, if you remember, or per thickness. Let's go to the equation. Here we call it the discharge QX, or this equation is QX per unit width. Okay, so here in the question says per kilometer. So that means that the direction perpendicular to the screen is 1 kilometer. So if I multiply this velocity, this discharge basically is not a velocity, that's it has the unit of m2 or length squared divided by time. If I it's it's a QX is the discharge per unit width. I multiply it by width, that is 1000 meter. that gives me 751 cubic meter per day, and that will be the daily discharge or volumetric flux from the aquifer to river B. Okay, so that calculation was for river B. We can do exactly the same for river A. The only difference here is the river A, the X value is 460 meter. That's all. So again, you apply the same equation. All the parameters is given in the question. Instead of X, you put 460 meter. Then you do the algebra here, the calculation. You'll end up with 1.27 square meter per day. Okay, and then the daily discharge, like before, you need to multiply that by 1,000 because the question is per kilometer. You multiply 1.27 times 1,000, which will be equal to 1270 cubic meter per day. And that was about the flow in unconfined aquifer, one-dimensional flow, unconfined aquifer under the steady state condition. Okay, I hope you found this video helpful. Thank you.